So, a very important skill if you're entering into a technical field is learning to solve problems. And there's a couple of strategies that we're going to be using to help us solve problems in this class. It's also important that when you solve a problem, you're able to communicate to other people how you arrived at your answer. In fact, that's critical. Anybody that's entering into a technical discipline almost always is required to leave a trail of documentation showing how they arrived at different decisions. And we're going to practice that within this class. Now, depending on exactly the task you're doing, you might be required to do this in different ways. So getting used to performing tasks in agreement with a particular procedure that has been outlined to you is kind of important, which is why we ask you to write notes in a specific way, and it's why we ask you to solve problems in a specific way. And this is something that you're going to have to do again and again and again throughout your career. So there are two major types of problems in chemistry. There are what we call quantitative problems, which involve doing numerical calculations, and then there are what we call qualitative problems, which involve describing things, normally using either language, written language, or symbols, perhaps diagrams. Often you'll have to do both of these things in the one problem. So you might have to calculate something and then you might have to explain something, or draw a diagram indicating how something happens and then do some math on that diagram. So it's important that you learn not only how to solve problems, but I mentioned this previously, but how to make your reasoning clear to other people that read your work later on. And this is, there's a lot of report writing that happens in technical fields. And, often, especially if we're dealing with people's health, we have to be very clear how we document things. So something else to be aware of is if you're writing notes, good notes always have example problems that illustrate how theory is applied. So you'll see me giving you guys example problems as we go through, showing you strategies towards solving different problems. So I strongly encourage you to include example problems in your notes, especially when we're doing numerical work. Sometimes people will just write out the formula, but they won't actually show how the formula is applied to real-world examples. So when you're solving a problem, often we rush through reading the problem. You always want to read the problem really carefully to make sure that you answer all aspects of the question. Not so much in an online environment. That's kind of like it's harder to miss answering the problem, but particularly when you're doing pen and paper quizzes and tests, it's easy to miss part of the problem. You want to make sure that you don't miss any information that might be provided to you within the text of the problem. And in the ALEKS environment, you have that data section, and that data section is really important to you. It has a lot of good stuff in there. Also, because this is an online class, you have a lot of information available to you via the internet, and it's really helpful to bookmark pages so you're not searching for them every time you need them, especially in quizzes and tests. You don't want to be doing that. The other thing you want to be aware of is that you're often, for numerical problems, asked to provide units very particular units, and sometimes you're going to be asked to give your answer to a particular level of precision. Sometimes this is referred to as sig figs, or what we call significant figures, and it's really a measure of how correct or how well you're able to measure something. So generally, once you kind of understand what the problem's all about, you've sucked all of that information that you need out of the question, you're going to kind of at least mentally, and sometimes we'll draw a little sketch, plan how you're going to get to your answer, right? And part of that planning process, like I said, could be sort of making sure the concepts that are going to be used. And in our case, what we really want to know is what we really might be thinking about is the sections of our book where we're going to find the needed information, or the parts of the data tables in ALEKS where we're going to find the needed information. And that's why in your notes, I often ask you to put section headings, right? So that you can very, very quickly find the needed information. So once you kind of like identify what you need and you've got a plan for how you're going to tackle the problem, then you get all of your information, you get all your data together. This could be numbers, it could be formulas, you know, those kinds of things. And then you do your calculations. Now, what we are going to do if it's a quantitative problem, what we're going to do whenever we do any quantitative calculation, well, we're going to use a process called dimensional analysis, which means that we will always include unit labels for every number that we're putting into our numerical calculation, all right? And I'll show you how to do this later on. So this is called dimensional analysis, and what the point of doing this is to make your thinking clear to others and also to help you detect any errors before you move on. So there have been many examples of, and we'll do a case study on this, of like horrible errors when doing dosing, when administering medications, right? And so by using this formula or this technique called dimensional analysis, you can detect those errors. And so that's kind of the point of it. It also means if something does go wrong, or for some other reason that somebody needs to look at your work, they can follow it through and they can see where you went right and where you went wrong very easily. Once you finish doing a calculation, you want to just check that everything is sensible. So for example, if you're calculating the length of something, like how long it is, right? Or you're calculating amount of time, or you're calculating the mass of something, right? It doesn't make sense to say, oh, I calculated that the height of the person is, 55 feet. That makes no sense whatsoever, right? You know that you've got that wrong because no human is 55 feet tall, okay? If you are calculating the mass of a hydrogen atom and you concluded that it was 15 pounds, you know that that's completely ridiculous because hydrogen atoms are a tiny little bit of matter and they don't weigh 15 pounds, right? If you were calculating the length of time that it took for a certain process to occur and you got a negative number, you would know that that was ridiculous and that you'd made a typo somewhere along the way because you can't have negative time. That just doesn't make any sense, right? So when you get to the end, you always kind of check your answer is like sensible. It's not some just like dumb answer. And if you do see that it's a dumb answer, then you can go back, and if you've done dimensional analysis, you should be able to pick up your error pretty simply. So what is this thing called dimensional analysis? Well, dimensional analysis is a technique where we use units to help confirm that we've set up our calculation correctly, and also to help illustrate to others how we did our work. And what we do in this method is the unit labels are treated algebraically. So we're going to multiply units, we're going to divide units, we're going to cancel units, all of those kinds of things. So what we do is we're going to take some numbers that we're given, we're going to do some math on them, and we're going to end up with a new number, right? And so in this process, what we do is we write what we're given on the far left of our page with its units. And then towards the right of the page, we write an equal sign, and we write what we want as far as the units a little bit after that equal sign to the right of it, right? So that will always be given in your problem. So you're going to take one thing and you're going to turn it into something else. So I might write like this. I might write 5 feet, and I want to turn that into inches. So that would be that was really bad, wasn't it? That would be my setup, right? I haven't got any numbers on the right there, but I've got my units, okay? So the given quantity on the left, then towards the right, an equal sign, and the units that I want to end up with. Then we're going to multiply our given quantity by one or more of what we call conversion factors. And what conversion factors are, these are fractions. And we'll show you what these are in a little while, but they're always a fraction. So I can immediately go ahead and put multiply and a fraction sign there. So in step 1, I do that. And then in step 2, I know that I'm going to multiply by some kind of fraction. Okay? And then what's going to happen is I'm going to do my math and I'm going to cancel my units. Now the fraction that I'm going to put in here, the conversion factor that I'm going to put in here, is going to have inches on the top and it's going to have feet on the bottom. And in that way, feet will cancel out and it'll leave me with what I want. And you probably know what this fraction is going to be. It's going to be 12 inches for every 1 foot. Okay? And so you can see there, 5 times 12, and then that's going to give me my answer there. It's going to be 60 inches. Okay. You can see by cancelling these units, anybody can very, very easily see that I've done this math correctly. So here would be an example, right? It says a tablet of aspirin contains 0.25 grams of aspirin. How many milligrams of aspirin does the tablet contain? And then we're going to give you the conversion factor that you need. You see, it's a fraction, isn't it? Conversion factor. Always a fraction. Okay, there we go. So, write the given quantity on the left towards the right, put the equal sign, and then the desired units, which we got from the problem. Then I'm going to multiply by one or more conversion factors, which in this case was real simple because it was given to me, to get my answer. So then I'm going to, in my third step, I'm going to cancel my units and I'm going to do my math. Okay? And the only units that are left over are the ones that appear in my answer. So it's not too difficult, right? You can see how it's super, super clear for anybody reading this what you did. And if you happen to make a mistake, it would be very, very obvious to them. Okay, so that concludes this section on using dimensional analysis in numerical problems, but we also talked about some strategies for solving problems in general. Pretty straightforward. I think dimensional analysis is arguably the most useful thing that you're going to learn in this first half of Chemistry 100. We use this again and again and again in Chemistry 121 and Chemistry 131, so it's going to be very useful for you as you move through your classes.